Thank you very much. I appreciate the invitation to come, so thanks for the invite. And today I'll be pleased to talk to you a little bit about some of my work and also some other work in low-temperature plasma physics. And so the title is Creating Order in a Disordered System. It's ultra-cold, strongly coupled ultra-cold plasmas. And I'd like to, of course, acknowledge at the outset the generous funding from the National Science Foundation and the Air Force Office of Scientific Research. So a couple of weeks ago, the Nobel Prize in Physics was announced, and it was awarded, it was shared by both Dave Wineland at NIST and Serge Haroche at the École Normale. And the citation reads here, for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. And here's the sort of perfunctory measure or picture of Dave Wineland in his lab pretending to turn knobs. It was funny. I worked for Bill Phillips during the time when he was awarded the Nobel Prize. Not because of anything I did, I promise you that. And but it's this kind of crazy thing because in the early days, Bill Phillips spent these amazing hours in the lab, working all the nights, all the weekends, turning all the knobs, hiring everybody. But by this time he hadn't. But they wanted to get pictures of him in the lab. And so you have to put up mirror mounts. Put your hand on this mirror mount. It won't do any damage. Anyway, he's a great guy. And we're all pleased that he's one of us. I want to tell you a little bit about his work. Mostly is to sort of lay the groundwork, give some context for some of the things that we've been working on in the last several years. So Wineland did a postdoc with Hans Stemelt at University of Washington. And after that, in 1972 or so, he moved to Boulder, Colorado, to work on the atomic clock. And the idea was, well, maybe we can take some of these ideas for ion trapping and apply them to laser cooling things, and maybe we can make a really good atomic clock. And so the ion traps that they started off with were these things that are called Paul traps. And this is a radio frequency trap. You basically have these 4-bar electrodes and some ions that are stuck there in the middle. And you want to apply some oscillating potentials to opposite sides. So this one and this one, for example, those are negatives, and these guys over here are positives, and they're oscillating. And what this does is this creates a quadrupole field for the ions that happen to be stuck in the middle. And although you can't see all the designations on this, but so if the top and the bottom here are the positives, the left and right are negative, you've got an ion that sits in this saddle point. It's repelled from the top and bottom and attracted left and right. And so you think, oh, okay, well, if I'm an ion and I'm sitting here, my job is to move away from the plus and move towards the minus. And so it starts to roll off one side or the other. But before the ion has a chance to move very far, you change the polarity of your field. And so you switch from this being positive and this being negative to that being positive and that being negative. And so the ion wants to roll off of the saddle point, but before it can roll away, you rotate the field and the ion is stuck. It has to stay there. Does this seem too bright to you guys? Is it painful to watch this? How about that? Is that better? Easier on the eyes? Okay, another Nobel Prize story. So it turns out that when you win the Nobel Prize, you get invited out to Stockholm, and there's this whole sort of week-long thing, maybe 2 weeks, that goes on before the Nobel Prize ceremony. And it's basically scientific meetings interspersed with drinking parties, or something like that. And so they invite a lot of other people. The Nobel Foundation invites a lot of other people who are kind of in your field, people who are your professional colleagues, to come give talks about their work and just to basically say how wonderful and amazing you are. And so Ted Hench was there in '97 when Bill Phillips won the Nobel Prize. This is my one connection. And Ted Hench is a laser guy, and he just loves to invent new lasers. And so he invented this super bright laser. This is before you could buy a frequency doubled YAG laser for $20. So he's got this thing as this monster, and it's got wires on it and everything. And there's no thought for safety. It's some pulsed, high repetition rate, intercavity frequency doubled, put your eye out, kind of burn a hole in the wall sort of laser. And so he's up there, like this. And after his talk, Claude Cohen-Tanuji, who also was a share of the Nobel Prize in '97, he gave the next talk. Colin Tanucci says, "Oh, Ted, can I borrow your laser pointer?" Ted's like, okay. And he hands it over to him. And so Tanucci, Colin Tanucci, he's this theorist. And he's up there, he's like talking, waving this thing all around. And somebody in the audience asks a question. And so he points to them. And the whole audience just like ducks for cover. So, all right, I'll use the wimpy one here. Okay, so anyway, so this is how the trap works, and not shown in this picture, you have a positive electrode on one end and on the other end, and that confines these ions radially. And it's a really great trap, except for this thing that happens, which is this Pondra mode of heating. So you have the ions that are always trying to roll off this hill, and the hill that keeps rotating underneath it, and that does some sort of parametric heating of the ions. And so you need to do something to try and take away that heating. And the thing that you do, one of the contributions that Dave Wineland and also Ted Hensch and Art Shallow in the 70s showed, was that you could use a laser, bring in a laser beam, and you can cool the ions while they're inside this trap. And you do that, it's kind of a little bit of a cartoon level-ish. You basically say, I have a photon, and the photon carries momentum, and I've got an object that's moving, and if I impart enough momentum in exactly the right ways, I can get this object to stop moving. The next phase of this cartoon is, let's suppose that you have a bowling ball that's rolling towards you and you want to stop it, but all you have is a bucket of ping pong balls. You can do it, but you have to throw them really fast and you have to throw them really hard, and so eventually you can get this bowling ball to stop. That's basically what they were doing. Photon carries momentum. You only push on the ion when it's moving towards you. And so that's what they do. You take this laser, and the momentum, there's a divider here. This is not new physics, so sorry about that. And yeah, okay, anyway, you have momentum transfer in the direction that the photon is heading. And so you can actually set the photon energy to be below the atomic resonance. And if the atom is moving, or the ion is moving towards the laser source, then it gets Doppler shifted into resonance with the laser beam, and it gets this little push. So you park the laser beam over here, and if the ion's moving this way, it sees that laser beam blue shifted into resonance, and it pushes on it until it slows down. Okay, so that's what they did. You kind of have this idea that your ions are moving until they hit the laser beam, and they go pow, and they get stuck in your trap. And there's some really actually amazing things that you can do. If you can trap your ions and you can cool them all the way down to just a shade above absolute zero, then you can do some things like this. This is a picture of a linear chain of ions in a Paul trap. And so what they have done is you load in some 29 ions in this case, and you shine laser beam on it, and they cool down and cool down and cool down until, in fact, you actually reach the 0 point almost of energy. So it's a harmonic trap, more or less, and you can take your ions and you can cool them down all the way to the global three-dimensional harmonic oscillator, your quantum mechanics textbook, n equals 0. So you've got h bar omega times a half, basically, in x, y, and z. And in this case, this so-called Wigner crystal, which is created, this occurs when you have this condition that the nearest neighbor potential energy just completely dominates over the kinetic energy. You've used the laser to take out all the kinetic energy, well, as much kinetic energy as you can get, not including the true 0 point energy that Syndrome got when he did The Incredibles. Did you guys see The Incredibles? Syndrome, a 0 point energy. I was going to be Syndrome for Halloween, but my hair wasn't quite long enough. But okay, so anyway, these ions crystallize. And one of the things that's really exciting, and I think one of the reasons why Wineland was able to share the Nobel Prize, was because you can actually do some operations with lasers on individual ions in this chain, and you can entangle the whole set of the ions. So again, I apologize, this is kind of a light touch, but the basic idea is that I have a bunch of ions, they're in a string, and they interact with each other. They interact with their trap, but they also interact with each other through the Coulomb force. And let's suppose I take one of these ions here, 3, and I use a laser beam to put it into some kind of a different internal state. And when I do that, I'm going to give some momentum to this ion. well, then what happens is that momentum that I give to that one ion, because of the Coulomb interaction, gets shared with all of the other ions in the system. And so then I have an internal state of the ion, which is now entangled with a global motional state of the chain of ions. And you can write this out. These are non-factorizable, truly entangled quantum mechanical states. And so this is a really amazing area of research that at NIST and Boulder and many places throughout the country they're putting significant resources into. And at Boulder they actually have working agreements with Semitech and other giant semiconductor firms trying to really miniaturize this. These are 440 screws here for scale. And then you use these lithographic techniques to try and make a pinning trap where all of the electrodes actually lie in a plane. And then you apply these RF fields, and you get these ions then that are trapped in little tiny strings just above the surface. And they want to try and do this in a real way, where you can put this in a chip, you can do laser cooling, you can individually address various ions in the chain. Oh, it's big news. Another kind of ion trap that Wineland used in his research, and that many people also use, is called a penning trap. So the Paul trap, this little linear RF trap, right? These 4 electrodes, and you put this oscillating potential on them, and it's this saddle point that you're rotating underneath all of your ions. But in a penning trap, it's a different idea. So you have a strong axial magnetic field, and then you have these 3 electrodes. And if you're trying to trap ions, positive ions, then you'll make this electrode and this electrode up at some high positive potential. This is a ground potential. And then your ions get stuck in this region. They don't move out towards the walls because any transverse velocity in the system gets pinned through the Lamour, the QV cross B, the Lorentz force into these Lamour orbits. And so you get these ions that are confined by the magnetic field as they travel back and forth in Z. And then the potential, these big potential hills that they can't climb out of at the end. And so this is kind of a interesting toy that can be used for trapping and manipulating ions. And so you get radial confinement with the magnetic field, axial confinement with the electric field. And of course, once you actually build one of these, they're not quite as simple as the cartoon shows, but the concept is more or less the same. You have segmented electrodes which allow you to do some other kind of interesting things. And so one of the really interesting things you can do is you can break up this electrode, and they did this in Wineland's group where they broke it up into 4. Right? The center electrode now has 4 different pieces to it. So one thing that happens, let me back up here, one thing that happens is that you have a magnetic field that points this way, and then you have these electric fields that are kind of fringing. And so your ions feel this QV cross B force, and they have this sort of drift. And so what ends up happening is the plasma, the entire plasma, then rotates. So there are 3 motions for this system. You've got the bounce motion, you've got the Lamour frequency, which is very, very high, and then you have the QV cross B drift, which is really slow. And so they said, we'd love to be able to control that QV cross B drift. You can say, why would you want to do that? And it's because we can, so let's do it. And so they segmented these electrodes and put very small potentials on here where they would put this up to some sinusoidal, so this one and the one behind it and the one back behind and this one in front. They would connect them to these sinusoidal frequency generators, and they would then lock the rotation. The QV cross B drift actually would synchronize up with the frequency that they applied. And that allowed them to do some really interesting physics to try and study what's happening. So, yeah.
Can you just for a sense of scale, can you say something about what the radial and axial harmonic frequencies are?
Sure, and it depends on the trap size, and obviously the potentials that you put on. But so the Lamour frequency is typically measured in some tens of kilohertz. The bounce frequency is around 1 kilohertz or so. And then the QV cross B drift is down another order of magnitude from that. Depends again on sizes and voltages and things like that. But sort of in the 10 to 100 kilohertz, then 1 to 10, and then 100 to kilohertz for the others. Okay, and so it allows them to do some really interesting things. And so they said, okay, I want to take a picture of these ions in the plasma. I want to see what they're doing. And so they would shine a laser beam up the bore because there isn't that much access, optical access. And so they, you have to be like Microsoft. Every time you run into a bug, you have to say, this is not a bug. This is a feature, right? I mean, we really intended this to crash every couple of days or so. Well, anyway, they took this, the bug, which was there's like zero optical access in this thing, and they turned it into a feature. They shine this laser beam that goes up on axis, and they use some kind of a fancy camera on the end to look at the scattered light. And this was the first picture that they published on this measurement. And so what you're looking at is this is a little beam stop that comes in. This is the camera, which is now looking straight down the bore at the laser beam. Most of the laser beam doesn't scatter. I mean, it just goes straight through the system. And so they put a block there to try and capture all that laser light. But then you get scattered laser light that comes out at all these different angular distances. And so this turns out to be something like a powder diffraction pattern. If you take some crystal unknown structure, you grind it up, you put it in your crystal diffractometer or X-ray diffractometer, and you can rotate it, and you see these kinds of things that occur. So with their rotating wall, they were actually able to synchronize flash, flash, flash. I'm going to synchronize the pulsing of my laser beam that does the imaging with the rotation of the plasma. So every time the plasma goes by, they'll take a picture, 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 picture. And they were able to then again look at, this is the diffraction pattern that's now time resolved. It's a stroboscopic, kind of measurement. And you can see these, beautiful diffraction peaks showing corresponding to a body-centered cubic system. They got better and better at this, actually, and they realized, I don't have to do Bragg diffraction. I can just, take a picture of the ions. And that's what they started to do, and then they could do some kind of interesting physics, condensed matter physics, using an atomic system. And so they were able to show, look, here's a nice face-centered cubic, here's another one, different orientation, here's your hexagonal close pack. And if you look, you start out here, and you have crystal discontinuities that end up going out in these different directions. And they were able to see these. They kind of get baked in as this crystal sort of grows from a little tiny seed. That's another interesting problem in condensed matter physics. And so in this case, once again, this is an ordered system that appears because of this energy scale. You have the kinetic energy of the system that's almost zero. And you have the potential energy of the system, which is very, very high. The electrical, sort of the Coulombic potential energy of the system. And it causes these planes, these crystals, to lock up.
What are the sizes? Go ahead. Oh, it's all right. I'm just thinking, what's the scale?
It's about 6 microns is the interparticle distance here. So 10 to the 15-ish or something like that. Okay, all right. Yeah.
So what determines which structure you get?
Yeah, it's a good question, and they don't really know. So if you heat it up and anneal it again, as it comes back down, you get a different structure. But it's kind of a crazy thing, right? We're going to anneal this by heating this up beyond about 2 or 3 millikelvin, and then we're going to cool it down again. So this is like,
Does this reflect?
yeah.
Does this reflect sort of ignorance about the true nature of the interatomic potentials?
No, actually, what happens? It's an interesting physics problem because so you can say, okay, I've got a system that's completely disordered. There's no order anywhere in the system. I've just got completely, gas-like. The correlation function just is flat. And then as I start to cool down, then this order starts to appear in the system. You start to get liquid-like structure. So near term, you have a little bit of order, but there's no global. And that starts to grow in little pockets throughout the cloud. And then as you continue to cool down, that order starts to, people start to influence their neighbors. But, if somebody in Utah Valley starts to build a grid system and then somebody in Salt Lake is building a different grid system, then when they actually meet, there's some, unconformity that happens. Right? It's that kind of a thing. Different parts of the the cloud are crystallizing and not the same way.
Is the temperature in the cloud uniform?
So that's another interesting question. So you start to ask, how do you define the temperature of the cloud? And so the temperature then is it's random sort of disordered motion that occurs in the local frame. And the temperature then appears to be uniform in the cloud. And for these, they're down about 1 millikelvin, maybe a little less, limited by the interaction with the laser between the ions.
What are the ions?
These are beryllium ions. It's a 2-electron system where when you ionize, you have a 1 electron atom left that's, depending on your sort of pain level when it comes to lasers, you can build a laser that talks to those as well. Right? So it allows you to do the spectroscopy on the ion. And that's mostly a historical choice for beryllium. There's another interesting thing, actually, another parallel track that Wineland was involved in sort of peripherally, and that was building nested pinning traps for the purpose of creating antihydrogen. And so it's a little bit crazy. So let's talk about this a little bit. So this is your friend, hydrogen, your proton that you know and love, the electron that you know and love. And when you look into the CPT mirror, then you realize this is going to go the proton to an antiproton and the electron into a positron. And there's a big question out there, which is something along the lines of, does the antimatter obey the same laws of physics as matter? So my advisor at Wisconsin, Jim Lawler, he did his postdoc with Art Shallow at Stanford in the late 70s, and early 80s. And there was an effort there to try and actually weigh a positron. So imagine this. Okay, graduate students back there, how many of you think you have hard projects that you're working on? Okay, so let's try to imagine this. I'm going to take a column, something like this, some big tube, and I'm going to put the whole tube at 4 Kelvin. That's not that trivial, especially, if you go back 30 years. And I'm going to take one positron, and I'm just going to drop it like that from the top. And I'm going to see if it falls down or if it falls up. It's antimatter, right? I mean, you don't know. Is it going to fall down? Is it going to fall up? I don't know the answer. And so the way the physicists love to do it is like, well, let's just measure it and see. All kinds of problems with this. Okay, so you happen to know that the ratio of the Coulomb force to the gravitational force, does anybody know that number? 10 to the 42, yeah, something like that. So this is, you can't even imagine this, right? So if you have this tube and there's a little patch charge on it, this totally messes up the trajectory of this thing by 42 orders of magnitude. And you have image charges. You know what image charges do? So if I have a proton or an electron or I have some charged particle next to a grounded plane, there's an image charge in the plane. And it gets attracted to the image charge. So anyway, my advisor said this guy who was trying to do this experiment never smiled. You can imagine why. Okay, so anyway, and so then someone said, well, okay, obviously we're stupid to use positrons. Instead of dropping positrons, why don't we drop an antihydrogen atom, right? Because it's like neutral. That'll be fine. Except that you can't buy them. I mean, you go to Walmart and the antihydrogen aisle is like empty. And so you have to try and come up with a way to try and make antihydrogen. And once you make it, then you have to try and figure out how am I going to hold on to it? When am I going to drop it? What am I going to do with this thing? So that's when all the laser physicists say, no problem. If you make it, we can measure it. Okay, so enter billions of dollars of research. And so they wanted to make this nested pinning trap. The problem with the nested pinning trap is that the positrons want to stay in the middle, and the antiprotons all want to stay on the outside, and that's bad. If you want to get people married, they need to spend time together. And, well, they don't have to, but it helps. It helps a lot. And so the idea was, okay, let's make a little tiny trap over here for the antiprotons. We'll put the positrons in the middle, And we'll just let them out so they just barely, they come down here and they just like roll over the top, slowly over the top, and then they'll come over here and maybe something good will happen over there while they're together. This is a project, again, this is at 4 Kelvin. You ask, where do you get positrons? Okay, well, you buy some, I don't know, sodium-22 with belts out these it's a beta plus, and then you use some kind of crazy tungsten moderator because you don't want like 2 MeV positrons. You want like 0 Kelvin positrons. All right, and so they come streaming in, and for the antiprotons actually come out of a accelerator ring at CERN, and so you live down in the bottom of this accelerator bay that looks kind of like this. Sorry for how pixelated this is. And work at 4 Kelvin. Your trap is never as simple as you want it to be. You've got 30 or so different electrodes that show up here. But you work at it really hard for a lot of years, a lot of graduate students and postdocs, and eventually you can write this paper in Nature Physics from last year, Confinement of Antihydrogen for 1,000 Seconds. This actually is a giant technological achievement, and we applaud the researchers who worked on this. Okay, so this is again an ultra-cold plasma, right? So this is an ultra-cold neutral plasma in this case, a neutral in some sense because you have both the positives and the negatives hanging around together. And you want something interesting to happen there. And you want a lot of interesting things, 1,000 babies per second. Oh no, that's 1 baby every anyway, lots of antihydrogen that are formed here. So we started to ask the question, what happens if you start out with a neutral plasma? Let's suppose that you take a bunch of atoms and you cool them down. You make them very cold, give them a temperature of about 1 millikelvin or so, maybe less, and then you photoionize them. What happens next? We didn't really know. Nobody knew. We talked to all these people. What will happen? They're like, I don't know. So we decided we would try it. So we'll introduce you to our system a little bit. We started out working in a thing called a magneto-optical trap, which is a neutral atom trap. And you make this by, this is kind of a standard recipe by now. You take 2 magnetic field coils. You run currents through them in opposite directions. And so the magnetic field, these dipole fields, point towards each other. And you get a 0 of the magnetic field in the middle. But the magnitude of the magnetic field grows radially out in every direction, so-called spherical quadrupole magnetic field. And you send in then on your plus and minus x, plus and minus y, plus and minus z directions, laser beams that are tuned approximately to resonance, a little below resonance from your atoms. The slide's maybe a little messier than it needs to be, but in one dimension, since the magnitude of your magnetic field increases linearly with distance in the spherical quadrupole trap, then you can pull out your quantum mechanics book and say, okay, if my upper state has total angular momentum of 1, my lower state has angular momentum of 0, then my upper state will split into these 3 different Zeeman substates, where the energy of the m equals 1 state increases linearly with distance, because the magnetic field increases linearly with distance on one side. It also increases linearly with distance on the other side, but points in the opposite direction. And so you end up with this Zeeman splitting, where m equals 1 goes up in energy here, down in energy over there. M equals minus 1, does the opposite thing. So then what happens is you bring in a laser beam. Laser beams point in from opposite directions, and they are spin polarized. Well, they're polarized laser beams, so that if you have an atom that's moving out over to this side, you send in a laser beam that is only tuned to drive the transition from m equals 0 in the ground state, m equals minus 1 in the excited state. And it only does that when the atom happens to be on this side of the trap. So the atom in the middle doesn't interact with the laser beam at all. But it moves out to the side of the trap, starts to scatter photons from your sigma minus beam, and gets pushed back towards the trap center. Once it gets back towards the trap center, it stops talking to this laser beam because it's out of resonance now. It moves out the other way, and when it gets far enough out the other side, then you have the sigma plus beam, so right-handed circularly polarized laser beam, and it starts to talk to this atom, scatters photons, and pushes it back to the other side. And you end up with an atom that's, depending on your parameters, is in a approximately harmonic potential rattling back and forth with a temperature depending on the system that's more or less given by the detuning of your laser beam from resonance. Okay, this is kind of what it looks like in our lab. This is vacuum system, shows up way inside. We've got lasers, lots of lasers that are not actually shown in this system. And if you were to look deep inside one of these little windows here, then you find this tiny ball of about 10 million or so atoms at about 1 millikelvin suspended by laser radiation pressure inside this magnetic field. Sometimes people will come and they'll tour the lab and they'll say, you're at 1 millikelvin, so like where's all the liquid nitrogen? Where's liquid helium? How are you going to get to this really low temperature? And the answer is that these atoms really don't talk to anybody except the laser beams. The fact that they have these very narrow resonances means that only the lasers can push on them. The black body radiation doesn't do much of anything for our experiments. Okay, so we put in a bunch more lasers and we take this neutral ball of atoms, sort of unsuspecting group of atoms, and we pump them up into excited states. We drive them up into the continuum, turn them into ions, and then use more lasers to do spectroscopy on the ions. You measure these fluorescence signals as a function of time, some kind of cool things, Rabi oscillations, block vector rotation, yeah, yawns everywhere. And so I know you didn't. I have to tell you, there was this guy, so I was a graduate student in Wisconsin. Did I tell you that I was a graduate student in Wisconsin? I was a graduate student in Wisconsin, and there was this guy who would come to the Colloquium. The Colloquium was always Fridays at 4 o'clock. And there was a guy who would sit right about where Brian Sam is sitting right now. And he wasn't on the faculty. He wasn't a graduate student. He was just some person, interested person, that would come in and listen to these colloquia. But about now, 40 minutes into the presentation, he would just let out this loud, oh! Sorry, didn't mean to embarrass you, but just brought back all these great memories of shivering in 12 feet of snow in Wisconsin. So. Okay, and you can fit this to a Voigt profile, and you can actually measure then what's going on with the ions. You can measure how fast they're heating, how rapidly they're interacting with each other, and there are time scales for these kinds of heatings. Some kind of interesting things, the ions that we make are not trapped, and so after we make them, there's some pressure. It's a radiation, well, it's not a radiation. It's a pressure that comes from the electrons in the system. These electrons then drive the expansion of the plasma. They're neutral plasmas, but because of the kinetic energy of the electrons as they sort of rattle back and forth in the potential well that pushes the plasma, drives the expansion. From the laser, we gave it to them. So we excite, that's right, yeah. So there's actually some kind of interesting things here. Maybe we'll get a chance to it. But so we make these atoms, we turn them into ions, and when we do that, your electron has zero kinetic energy, if you're right at threshold, zero kinetic energy at infinity. But they don't get that far before they start interacting with everybody else. And so they start to pick up some, they push on each other, and that energy then drives this expansion. It was something that wasn't really obvious from the beginning. There's another heating mechanism, actually, which is three-body recombination. So the electrons and ions at zero temperature then recombine and form neutral atoms. That is a three-body event, and that also heats the electron system. And so that helps to drive this expansion out. Yeah, question?
Do you see something like a sound wave where the ions sort of lag?
Yeah, oh yeah. So this is ambipolar diffusion, but there are some really interesting things, some shock waves that can occur depending on, so if you give the electrons like a lot of energy, then the electrons all sort of, because it's this delta function in energy initially, and so they all try to leave, but they can't. So they get called back by the electrons through this Coulomb interaction. But that initial jolt of energy then can lead to shock wave formation out at the edge of the plasma. And there are other things actually you can do. People have, and we've done some of this work where you will illuminate the plasma with some kind of a radio frequency pulse, and you can help heat and drive the expansion as well. There's another sort of interesting thing that happens right here, and that's this very rapid expansion. So our RMS velocity for the ions when they're first created is down here at about 1 meter per second. And on a very short time scale, they heat up, and their temperature goes up by something like 3 orders of magnitude. And this is a thing that we call disorder-induced heating. It's because we ionized a system that initially had no order. All the ions, or the neutral atoms, are initially sort of randomly spaced relative to each other. And when you ionize them, you impulsively turn on this interaction. You impulsively harden the potential that these particles are interacting with. And so that leads to this disorder. And this disorder-induced heating actually is all related to the density and the coherence, the correlation structure factor of the system. Okay, so now you can say, so what's interesting about this? And there are some really actually kind of fascinating things about this. And so we need to take a little break from atomic physics. We need to go back to your sort of 4th semester physics class, where we talk about like modern physics and scattering and tunneling and fusion and things like that. Turns out that our ultracold plasma systems have some things in common with plasmas that have some technological applications. So here's a story. You all know that if I have 2 nuclei and they're going to collide together, that we're just going to write out a potential energy. And so this is the cartoon for the potential of the nuclear scattering event. There's this barrier for the potential, and then there's this binding energy. The barrier for the potential is something like 1 MeV, and the binding energy sits down here at minus 30 or so million electron volts. And so suppose I have, and for temperature scale, 1 electron volt's about 10 to the 4 Kelvin. So 1 MeV is like a lot of Kelvin. 10 to the 13 or something. But anyway, you don't have to get to those 10 to the 13 Kelvin for fusion to occur. Or 10 to the 10, Kelvin for fusion to occur. What ends up happening is you get a nucleus that will, 2 nuclei that will collide on some trajectory. And as they roll up this potential hill, because it's a quantum mechanical deal, there's a certain probability that this particle will penetrate through the barrier and go inside of this nuclear barrier, and it will be trapped. And we call that fusion. And there's this probability that you can calculate using WKB formalism and all of that. It turns out there's this transparency coefficient that goes like e to the minus square root of the gamma of energy over the, this is the kinetic energy then of the system, the particles as they collide. And what you find out is that your gamma of energy, named after our buddy Gamov, who calculated this, is also on the order of 1 MeV. And so, if you have particles that are even, 1 MeV or 10 MeV, you're going to be, you'll be okay. So you get fusion in the sun, even though the sun is not as hot as, to take you over the top of the barrier. Okay. So we, just for fun, thought to ourselves, what about in our systems? What are the probabilities that we could actually, have this tunneling occur in our system? And so we thought, okay, this is no problem. Transparency factor, we're at 1 million electron volts, or at 1 millikelvin, so that's like 10 to the minus 4. We'll do 1 Kelvin. 10 to the minus 4 electron volts gives me e to the minus, you have to square root, e to the minus 10 to the 5, that's 10. That's 43,000 zeros and a decimal point, 43,000 zeros and the number 1. That's a really small probability. So we're not really doing fusion. But there's an interesting thing that can happen. In our system, it's neutral, and the electrons can do some screening for us. And what that does is it reduces the interaction energy and allows ions of a given energy to get closer to each other. And in fusion plasmas, actually, this turns out to enhance the fusion probability. So here's our cartoon again. If I have some screening, what it does is beyond the screening length, it reduces the interaction. And so ions that come in, they roll in, they actually get to a closer distance before they're turned away. That's what the screening does. It is as though the ions had this little extra boost, because without the screening, they'd have to have this extra energy to come in. Well, anyway, if you do the WKB approximation, you realize that this probability goes like e to the minus the integral of the energy integrated over the barrier width. And so if you can get a little bit closer, then you exponentially increase your probability of fusion occurring. So it turns out that this collision, the fusion cross-section, which roughly you can write this way, picks up an extra term when you have shielding, and that shielding is exponential in this gamma, which is the ratio of the nearest neighbor Coulomb potential energy to the kinetic energy of the system. So when this number is bigger than 1, then you say you have a strongly coupled system. Those pictures that I showed you of those crystallized ions, those had numbers where gamma was like 100. And so you start to think, oh, this would be great, right? I mean, e to the 100 is like a really big number. But you have to remember that, at least for our systems, we're talking about e to the minus 100,000. So e to the 100 doesn't help you out any. But just for fun, we decided, well, let's try and calculate this. What densities do we need at our temperatures? You know, for this to happen, you need, you know, something like 10 to the 13 of the density of lead. So not so good for ultracold plasmas. But this idea that you get exponential enhancement in the thermonuclear fusion rate has been around for several years and is really hard to measure. In calculations of the luminosity of carbon-rich dwarf stars, for example, white dwarf stars, you see more energy coming out of these stars than you should get just from purely temperature. If you just think about, I've got so much density, I've got so much temperature, I can calculate the fusion probability, and you get a lot more energy out than you should get. And so there's some evidence that says that you get this exponential increase. There's your white dwarf star in this phase diagram, and you get these strongly coupled effects where you get this e to the gamma enhancement. So it's interesting. So we're not going to do fusion in our laboratory, I promise you that. We don't have 10 to the 13 times the density of lead, and we don't really have, 10 to the 85 million times the age of the universe to wait for things to happen. But there's some interesting analogies that occur. One thing that we have been really pushing on in our lab is to try and figure out, well, what is it that in atomic physics looks like this exponential enhancement of close collisions? What is it that's going to do that? So Dan Dubin at UCSD has done a lot of work in these pinning plasmas, pinning traps, and what he said was, what they noticed is that the energies of the system can be broken down into energy for motion along the field lines and energy that's locked up in the Larmor frequency, right? This little gyromagnetic oscillation that goes around the field lines. And so this E parallel, this kind of motion, and this E perpendicular, which is the rotation motion, they are mostly conserved and almost entirely separately. They don't interact. It's hard to transfer energy from the Larmor precession to the perpendicular or to the parallel motion of these ions. And it's because there are these adiabatic invariants. It has to do with the conservation of angular momentum. So if you get these two ions, they're like spiraling around the field. They have a certain amount of angular momentum. And when they collide, it's an elastic collision. And so they will like interact, spiral out to some big radius, but then when they pass each other, they go back exactly to where they were. And so this rotational motion, longitudinal motion, don't really talk. But it turns out that, that at high enough temperatures, then these adiabatic invariants go away. But at very low temperatures, then this adiabatic invariant appears. And so you don't get the equipartition, actually, between parallel and perpendicular portions of the energy. That equipartition rate, which is plotted here, just goes down through the basement sort of exponentially as you get to low temperatures. And we're going to start, these ions at 1 Kelvin. Maybe we'll go down to some millikelvins, and so then it's essentially zero. The equipartition rate goes to 0. So Dubin said, well, let's take a look at this. And he showed that there's this analogy. So in a fusion plasma, you have ions with some energy. You have potential energy stored in the nucleus, and the electrons do the screening of the ions. And their collisions that actually lead to fusions are really rare. And they liberate a lot of energy. In a pinning trap, you have, the analogy is that you have ions with a high level of parallel energy in the motion along the magnetic field lines. And you have a lot of energy that's stored up in that circular, the gyromagnetic rotation. And the magnetic field in the system actually simulates the confining force, that neutralizing screening that goes on. And you have these rare close collisions that will serve to equilibrate the energy perpendicular, parallel and perpendicular. And what he observed is you get this exponential enhancement of close collisions. This is a result of a simulation that he ran. These are in units of the plasma frequency, which in their system was, in the simulation, was close to this gyromagnetic frequency. And so he said, all right, we're going to put a lot of energy into the rotation. So orders of magnitude more energy into the rotation and just a little bit of energy into the longitudinal. And we're going to let this thing go. And we're going to plug in all the important physics and see what the simulation tells us. And so you'll go along happily, and the energy here, even though they're separated by orders and orders of magnitude, 2.5 orders of magnitude, doesn't change at all until you get a rare event, a rare collision where these guys will collide with one another and maybe in the presence of something else so that you can change the angular momentum of the system. And then you go along for another 20,000 or so steps, cycles of the frequency, and then another one, and eventually you get this thing that will happen. And so you say to yourself, okay, so if we're working in ultra-cold neutral plasmas, what is it then that looks like this kind of crazy exponential enhancement for the close collisions? What's the signature that we can look for? So let me just tell you quickly here at the end a few things that we've been looking at. One thing that depends on close collisions is our three-body recombination. For a non-neutral plasma, there is no recombination because there are no real electrons. The screening is all done by this the magnetic field, which in the rotating frame looks like a neutralizing background charge. But in our system, we've got like real live, honest-to-goodness electrons, and you can calculate out what the three-body recombination rate ought to be. And using some fairly straightforward physics, you get the three-body recombination rate coefficient needs to scale like the density squared and temperature to the -9/2. And this has been tested over a lot of orders of magnitude in both density and temperature, and it looks like it is good. But something breaks down because when you have a strongly coupled system, then you're always in collision. That's what the strong coupling means. These particles are locked up into a Wigner crystal, and they're always colliding. And so what does this mean when you have, what does recombination even look like in a system like that? So we took some data, just briefly here. This is, we create our neutral plasma, and instead of sending lasers in to provoke it even more, we actually just wait and look at the fluorescence that comes out. So these lasers promote up to the continuum, recombination occurs, filter down through these Rydberg states, and eventually belt out a visible photon which we can measure. And so we measure that, and this is the rate. You see the three-body recombination it goes up, the rate increases until the plasma starts to expand, and when it expands, the density falls and shuts off the three-body recombination. We can measure this over a bunch of different temperatures and densities. Doesn't really look that promising. I mean, these all have like different time scales. But it turns out that if you scale everything by the density, and it's the rate coefficient that goes like density squared, and so the total number will go like density cubed. So if you scale everything by density cubed, then here at the beginning you have all of your experimental measurements showing up on the same sort of universal curve. So we we make measurements of this, and we ask, so when does this three-body rate, which is basically proportional to that slope with some approximations, when does this start to change? And so at relatively high temperature, electro temperature is about 57 Kelvin, then it seems to scale like density cubed the way it's supposed to. 30 Kelvin seems to scale like density cubed. But then as we get down into very low temperatures, a half Kelvin or so for the initial electron temperature, then the scaling changes. This coefficient is no longer density cubed, it's something else. So this begins to look like the onset of this many-body interaction, right? The fundamental description of three-body recombination has changed. But it's not this exponential enhancement that we were looking for. It's some crazy thing. Perform some simulations, calculate what the three-body recombination rates ought to be, and everything looks good. We think we understand the physics here. And the slowing down here of the recombination rate looks like it is due to, once again, this sort of onset of this many-body interactions. There's another thing that depends on close collisions, and that's this disorder-induced heating. Remember that fast rise in the temperature of the ions right after ionization occurs. And that's a kind of nearest neighbor interaction. You can put up a fairly simple model. You say, let's suppose I have two particles that are separated by some distance. Then the force on them in some unit system just goes like e squared over the distance squared. And the acceleration then is the force divided by the mass. And again, this starts to look like the distance between ions in the plasma multiplied by the plasma frequency squared. And so we can then measure sort of the rate at which the nearest neighbors start to push on each other as we change the electron temperature. Because in this picture, the electrons, if they're starting to do their job and screen out nearest neighbor interactions, you would expect things to slow down. So this is what we measure. In this plot, this shows you, this is the electron temperature, and this is the ion temperature. And as the electron temperature goes down, the effectiveness of the electrons at screening out their neighbors gets better. Right? The electrons do a better job of staying close to their parent ion and shielding out the interaction of the neighbor. And so, so what you see then is this temperature for the ions goes down and down and down as the electron temperature goes down. The other thing that happens is that the time scale for the heating to occur increases. And this goes up, up, and up, and up. And so we are actually kind of excited about this because this begins to look like some kind of exponential increase that we were looking for in our system. Okay, well, let me wrap up. I've told you a little bit today about non-neutral plasmas. We talked about Dave Wineland, the man, and the work that he did in non-neutral plasmas where he trapped ions. Some of them trapped them one at a time for doing quantum logic and looking at crystallization in chains, linear chains of ions, and also groups of ions, some millions of ions that would be trapped in these Penning traps. Again, looking at ion crystallization, there's some really interesting work that's done that has this analogy with fusion plasmas that comes out of these Penning traps. And I've told you something about some of the work that we're doing at BYU where we look at ionized laser-cooled gases that are also in this kind of same temperature and density regime as the non-neutral plasmas. And there's some hints of some really interesting physics. There are some, we're exploring to try and find what is it that's in this system that might also have some analogy with the behavior of these fusion plasmas. Some, not because we're doing fusion, but because we want to explore the behavior of strongly coupled systems in this technologically interesting regime. And I think one of the things that's really exciting about it is this kind of this overlap. This field that we're working in is really the overlap between plasma physics, atomic physics, and condensed matter physics, where you really can look at the work and the results through any one of these different lenses, and hopefully we can do some really interesting physics on that. And with that, I will conclude. Thank you very much for your attention.